A relevance score can look accurate and still rank the wrong document first. RankNet's Pairwise loss trains a PyTorch scorer on which results should win. You'll learn how the pieces fit into a workflow that learns document preferences and checks whether ranked results improve. I'm Professor Pi, teaching AI foundations with simple Python. Search and recommendation boil down to order. You can score items independently and still show the wrong thing first. RankNet fixes that by training on pairs. It learns which item in each pair should come out on top. That matters when users care more about the top of the list than raw scores. People reach for RankNet when clicks or graded labels give you reliable relative preferences, not absolute targets. Imagine two documents for one query. You want the model to prefer the more relevant one, not just assign a plausible number. RankNet turns that preference into a loss. If the weaker document ranks above the stronger one, the loss pushes the model to flip them. It does this by taking the score difference and applying a logistic-style loss, so the model widens the gap in the right direction. This is why RankNet often helps with top K quality, even on modest examples. We will build a tiny PyTorch flow that shows the problem, converts labels to pairs, trains a tiny scorer, and reports a ranking metric so you can see improvement. The goal is clarity, not a production system, so each step stays visible and easy to follow. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now, we'll create a minimal failure case, so the need for pairwise learning is obvious. This snippet builds the smallest visible ranking failure with PyTorch tensors. The scores look reasonable on their own, but the highest score maps to doc's int scores argmax, which is not the most relevant item in rel. That mismatch is the pointwise pain we want to fix. The X tensor holds simple query document features we'll reuse later, instead of rebuilding data. And the printed top doc and true rel make the ordering mistake immediately visible. That mismatch makes the next step obvious. We must turn single labels into pair comparisons, so the model trains directly on preferences rather than absolute targets. This example converts relevance labels into the pairwise comparisons RankNet actually trains on. Each row in pairs expresses that the left document should outrank the right, so diff becomes the score gap the model must push positive. torch.nn.BCEWithLogitsLoss is a natural fit because RankNet uses a logistic preference loss over those differences. Target is all ones, since every constructed pair prefers the left item, and the output prints pair loss and the average preferred prob, so the ordering error becomes a measurable quantity. With pair construction in place, the obvious improvement is to stop using handcrafted scores and let a model produce them. That swaps manual numbers for learnable parameters we can update with gradient steps. This code replaces the handwritten scores with a tiny PyTorch model scorer. A torch.nn.linear layer is enough. Features go in, a single score comes out, and argsort turns those scores into a ranking. The weights are initialized so the untrained scorer still ranks poorly, which keeps the problem visible before training. Start saves that initial ordering for the final NDCG comparison, and the output shows which document the fresh scorer prefers as our baseline. Seeing the baseline, the training loop itself must compute score differences from the model and use them with the pairwise loss. The crucial detail is to recompute predictions each iteration so gradients flow through the score gap properly. This snippet performs the actual RankNet training step with PyTorch. The loop recomputes pred from the scorer, builds pairwise score gaps using pairs, and minimizes loss FN on those gaps, rather than fitting absolute labels. Loss backward and torch.optim.SGD, updating scorer parameters, move the weights so preferred documents score higher than non-preferred ones. The LR controls how big each step is. Too small is slow, too large can overshoot, and the printed output shows the trained ranking now starts with the best document, which is exactly what the pairwise loss encourages. Once training changes the model, what really matters is ranking quality, not the loss value. We need a metric that rewards putting relevant documents at the top and makes it easy to compare before and after. This code closes the loop with a ranking metric instead of another training loss. NDCG at 10 scores putting high-rel documents near the top and normalizes against the ideal order, so the result is easy to compare. PyTorch tensor ops compute both the baseline from start and the trained result from trained without pulling in another library. On larger systems, you apply the same idea per query and average across queries. The output shows the trained RankNet scorer improved NDCG, linking the pairwise loss back to the ranking outcome viewers care about. In a real project, you would repeat this per query across many queries and average NDCG. You would also sample pairs carefully to avoid quadratic blowup and to reflect user behavior in the pairs you train on. To summarize, RankNet trains on pairs, so the model learns preferences instead of absolute scores. Use it when top K ordering matters, and you have comparative signals or graded relevance. One caution, pairs can explode combinatorially and introduce sampling bias, so pick pairs and batch sizes deliberately. A clear next step is to train the same flow on a larger labeled corpus, for example MS Marco pairs, and tune the learning rate along with pair sampling strategy to maximize NDCG on a held-out query set. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.